Hi everyone. This talk is about abductive reasoning in intuitionistic propositional logic via theorem synthesis. Let me start by overviewing it. So what we do is that we synthesize minimal assumptions under which a given formula in intuitionistic propositional logic becomes a theorem. For that, we have a compact Prolog-based intuitionistic logic theorem prover. And by putting all those things together, we get actually an abductive reasoning mechanism for intuitionistic logic. And one step further, we get a generalization of abduction. We synthesize sequent premises using a set of canonical formulas that cover via reduction mechanism arbitrary intuitionistic logic formulas, but they are small compared to arbitrary formulas and then expressive enough. So by synthesizing just those, we kind of cover everything that is missing from a formula to become a theorem. And of course, the paper is self-contained literate Prolog programming, fully replicable, and the code is available at this link. Okay. Our inspiration, well, the truth tables of classical logic, everyone knows them. Given a formula F in classical logic, each row in a formula's truth table describes a conjunction of literals. Here is an example. That's our formula F. That here is its truth table. And now if we select one of the rows which end up with a 1 here, then if you consider the implication, if this is true, this is a disjunction of any of those, so if one of them is true, then the result would be that the formula G implies F is actually always true. It's a tautology. So we interpret it, of course, as A and the norm B and C. So the natural interpretation of ones and zeros here. And then the tautology is shown as the formula implying F. Now, what's important about this is that we have a very simple way, in fact, given a truth table, which is particularly, well, not always easy to make. Of course, it's NP-complete, co-NP complete thing to make an arbitrary truth table and check that it's a tautology. But once, or if you have it, then it's very easy to take any of the lines here and turn the formula into a tautology by making it as an assumption. So now the challenge is, can we do that into a logic that doesn't have truth table and moreover, contrary to classical logic and any of the intermediate logic, well, an infinite number of them, in fact, exist. Gödel pointed that out a long time ago. We do not have finite truth tables. We do not have interdefinability of logical connectives like we have in classical logic. Well, let's say implication and zero are enough to emulate everything else, or NAND alone is enough, or NOR to emulate all the other connectives. So we do not have also a rule of excluding middle, which speeds up some classical reasoning, but loses, of course, the constructiveness that intuitionistic logic brings. So all we have is really a concept of tautology, which is when the theorem prover can prove it, and contradiction when it fails to prove it. So in intuitionistic logic, we need to find assumptions that would make the formula a theorem. So such assumptions include conjunctions of literals. That's the closest thing mimicking the truth tables of classical logic. But it also makes sense to extend them to more expressive subsets of formulas, which we will do a little bit later in a deeper way. But here it could be that it's maybe interesting to see a chain of implications, for instance, or disjunction that if we assumed under that condition, the formula would become a theorem. So for that, we need a search process, and we would like that our assumptions are minimal with respect to the partial order relation governing the logic, which is intuitionistic implication. Can look at it as a Heyting algebra, and then it's the corresponding operator to the implication, forming a lattice structure there. Well, another inspiration here is, of course, abductive logic programming, which has a subset of the available facts. They are designed as being abducibles. They are filtered with integrity constraint to provide relevant assumptions needed for the success of a goal with respect to a given program. In the context of intuitionistic logic, our abductive reasoning algorithm will rely on finding minimal assumptions under which a formula becomes a theorem. But because we do not have the truth table mechanism or decision procedure, like for Horn clauses, in this case, that's simple enough. We need a theorem prover for that. So in the absence of a convenient automated semantic method, we will then have to bring you a simple and easy to play with in Prolog theorem prover. And that's what we do next. We have here a very nice G4 IP sequent calculus that it has been implemented, in fact, in Prolog, a much kind of larger program and a bit more complicated that you will saw next. And it has a very important property, which typical sequent calculi do not have. Termination is ensured via multi-set ordering, so no loop checking is needed for those formulas. And a particularly interesting one is the sequent rule here that breaks this difficult implication type in which an implication implies something else. Because this maps to be the Curry-Howard isomorphism to types. In fact, this would be the type of a function applied to something else would. So it's like basically the higher orderness is a little bit difficult to deal with. Both in the type system and then as formulas, and this gets broken up in smaller formulas. So that's one of the key things that we use. The other are almost naturally mapped, provided that you have a simple rule when you translate to Prolog. This here becomes the head of the clause, and this becomes the body of the clause. So you read those formulas backwards, because they say that if this is true, then that is true. But in a goal-oriented sense, you would say for this to be true, those two need to be true. So here's the Prolog code coming out from that. Case analysis, we added also a few operators that are not part of the original calculus, just because they are very convenient. Negation is added directly here, and then We have also the equivalence relation, which is very useful to express equiprobability, in fact. And then we have also the reverse implication, which is what we use in Horn clauses, so reasonably good for a Prolog programmer to see sometime implications backwards. The prover does a bit of case analysis on this part here is the breaking of the complex constructs, including the one that I mentioned. And then the prover is recursive, but it's reasonably efficient. And then we have an interesting property via Glivenko's theorem, of course, that the double negation of something, if it's intuitionistically provable, then it's also classically provable, the original. So with that, you have actually classical logic for free. Not the most efficient, of course, for classical logic, but convenient as a one-liner in our self-contained code here. So if we want now to emulate classical abductive reasoning, we will define some atoms occurring in a formula as the only ones to be used in the search process. And that basically allows us to restrict the search for assumptions made only of abducibles. Sometimes in a practical situation, you know what kind of premises you care about for that. So we have the protasis generation, that's the search for premises here, that would work on a subset of the abducibles and their negation. By default, everyone is abducible, but it's more interesting if, again, that can be restricted. So what we do here is that in a way we are mimicking truth tables. And for that, a conjunction of assumptions would be what we would like to have, very much like in the first slide that I showed you with one of the members of the disjunctive normal form that corresponds to the left of the truth table has been used as a prerequisite for a formula to be a tautology. So among the assumptions that we find, we would like to make sure that we can find the weakest one. And for that, we rely on a total order given by the, on a partial order given by the intuitionistic implication. This order is total in classical logic because either P implies or Q implies P. That's a theorem. And then we don't have that property in intuitionistic logic. So we have a partial order here. For Peirce's law, we obtain an interesting weakest protasis here, which is P or negation of P. And that's actually one of the ways to turn intuitionistic logic into classical logic. If you add this as an axiom to the axioms of intuitionistic logic, then you hit classical logic. Of course, Peirce's law is also an alternative axiom that you could add to intuitionistic logic to turn it into classical logic. Now, another interesting logic is the logic of here and there. It's derived from intuitionistic logic by adding this axiom. That's in one of the nice papers by Vladimir Lifshitz. So if you add this axiom, then you turn the logic of here and there. You turn intuitionistic logic into the intermediate logic of here and there. So the weakest protasis in this case, when you call it, will say something a bit milder than what you have seen here. It means that for those two that come in this formula, the tertium non datur, well, the excluded middle needs to hold. So that needs to hold here, or this needs to hold there. So relatively interesting weakest assumptions that we can infer to see what would make some interesting formulas into theorems in intuitionistic logic. And in this case, two interesting cases would be classical logic and then the logic of here and there. That's, by the way, used as a foundation of answer set programming. A very simple example now here, a classic one from the Wikipedia actually, is how you explain given a prover and a set of abducible and a program and integrity constraint set and the given goal, what explanation you could derive, what the explanation in this case would be the premise that you need to add for this to be a theorem in intuitionistic logic. So how we do that, we find any protasis given the abducibles. We ensure that we explain the goal, so the program should imply the goal here. And then we ensure that the integrity constraints hold, so the explanation and the program should imply the integrity constraints. And then eventually we do not want a contradiction that explains everything, right? That's too much. We want to make sure that the explanations and the program do not imply false, which would be a contradiction in intuitionistic logic as well as in classical. And this is our constraint on that. So when we have this little query about why something is wet, sunny, and rained, and sprinkler, and we have either that there is a sprinkler or it has rained, and then the goal would be what we observe, that the lawn is wet. So now we would like to run it and see why it is wet, right? With the intuitionistic prover, you can replace the prover here with a variant of it, like or a classical one. In this case, they would agree. And the program would be that it's sunny and it either rained or the sprinkler started, and that's why it is wet. And then the integrity constraint that tells us, which is it in fact, is that it is not true that it is rained and is sunny, right? So if it's sunny, it cannot rain, allegedly. So the explanation would be then it's the sprinkler and it has not rained, coming out as the protasis that our program synthesizes. And now the more interesting thing here, and we are a little bit out of time, but by just looking at those interesting formulas, any more complicated one can actually be replaced by those. So here we have the weakest premise. That's from one of the seminal papers by Gregory Mills. And then what we want to very quickly discuss here is that logic programming, ASP, SCASP share as a key idea the fact that you want to synthesize a model. So models are a set of facts that hold under assumptions described by a program, and then here we actually find a mechanism to see what kind of assumptions form something that looks like a model that explains or that makes sure that in intuitionistic propositional logic something becomes a theorem. So our conclusion, as we are running out of time, is that we provide a generalized view of abductive reasoning as an instance of program synthesis controlled by a theorem prover. This can also be applied to equilibrium logic and other intermediate logic, particular also to modal logics and alectic, temporal, deontic, or epistemic systems. This generalized abduction synthesis could reveal critical missing assumptions, not just as literates, but also as a conjunctions of interdependencies among them. So in that sense, it's a bit richer than abductive logic programming. In a way, it's one step towards inductive logic programming that would synthesize explanations that are richer in terms of being snippets of programs that explain a set of facts. So that is my talk. Thank you very much. And ready for questions.